changes to argon. Rubidium changes to strontium. Samarium is a rare earth element, is radioactive. It transforms itself to neodymium, another rare earth element. And carbon, some carbon is radioactive, that's carbon-14. It transforms itself back to nitrogen-14. So those are some of the radioisotopes that are useful. Assumptions, again, closed system. Beginning quantities are known, constant rate of decay. All those three things have to be stipulated. Some type of closed system assumption, the beginning quantities are known or can be inferred in some way, and we have constant rate of decay. The rate project and the rate researchers have been doing some studies, and that's here's the committee, the rate committee, 1, 2, 3, 4, 5, 6, 7. Okay, and we have the rate research project. I'd like to tell you a little bit about what some of the things that the rate project has done. Radioisotopes at the age of the Earth. We're testing the assumptions of radioisotope dating. We're developing alternate models for interpreting radioisotope dates and data, and we're writing technical reports. That's what's been going on. Research group goals. Current rate projects, it's like a giant jigsaw puzzle, kind of putting together pieces. How are we going to put together the radioisotope data in some type of coherent way? There's discussions of theoretical models for accelerated alpha and beta decay. Dr. Eugene Chaffin's work. Search for dating concordance and discordance. That's what I'm working on. I'm searching, or testing rocks for concordance and discordance of the dating techniques. Search for decay traces of short half-life isotopes in rocks, especially that radio halo work of Dr. Andrew Snelling. Measurement of helium diffusion in minerals. Dr. Russell Humphreys, primary investigator there. Measurement of helium and argon content in minerals, and that's being done also by rate researchers, and in measuring C14 in coals, and maybe even in diamond. It'd be fun to measure some high carbon content materials to see if there's any measurable C14 in those. Those are things that are going on, and you'll probably see those in the final report. Some interesting results: very high abundances of radioisotope decay products occur in some minerals, especially those zircons. Remember that Dr. Vardaman talked about. Different dating methods often give discordant dates for the same rock or mineral. And I've been working on that, and it looks like it's usually give discordant dates for the same rock or mineral. I'll give you some information on that here and before I finish. And then radiogenic gases, argon and helium, occur in larger quantities in minerals than conventional dating methods assume. We're finding out argon associated with the zircons especially, or the helium with the zircon, and argon associated with potassium. Helium diffuses rapidly from minerals. How can helium and decay products be so strongly associated with these minerals? And then halos of short half-life elements occur in many common rocks, suggesting rapid crystallization of these rocks in some way, either by fiat creation or by rapid igneous process. So the halos are something that's very interesting. Let me tell you about my work here. Okay, mineral isochron method applied as a test to the assumptions of radioisotope dating. The ultimate date that a geologist would feel confident in is what's called an isochron date, or an isochron method. You date or measure the isotope ratios of multiple rocks in a cogenetic unit, or you measure different minerals in a single rock, and you plot those on a graph and use the slope of the line to indicate what's called an isochron, and then estimate the age. That's the ultimate dating method. And the age of the Earth is currently 4.54 plus or minus 0.02 billion years, according to the lead-lead isochron, which is a sloping line formed from meteorites, of all things, the lead content of meteorites. And it's not the age of the Earth is really done on meteorites, the current estimates. But the isochron method is the favorite method for dating things. So I've been involved with my own isochron dating. Dates on Bass Rapids Diabase Sill in Grand Canyon. There you see the Grand Canyon block diagram. And one of the units down in the bottom of the Grand Canyon here is the Diabase Sill, this Diabase intrusive in the Hackatai Shale. And I've been able to collect that with Dr. Andrew Snelling. We have sampled that, and together we are measuring the isotope ratios of various rocks, about 11 different rocks, and minerals, up to 7 minerals per rock in the Diabase Sill, Bass Rapids Diabase Sill. It's intruded between strata, so it has to be younger than the strata that it's contained in. It's rapidly emplaced because it shows evidence of forceful injection, and because it couldn't intrude itself slowly, it would segregate into different mineral phases. It's very homogeneous material, and because it's very homogeneous material, it lends itself to the isochron dating assumptions, and it's ideal for whole rock and mineral isochron dating. It's has strong enough evidence, I think, to convince any creationist that it was once in a homogeneous or thoroughly mixed isotopic state. And so the different isotope ratios that may exist in it now need to be interpreted, I think, even whether evolutionist or creationist, in terms of the idea of a homogeneous, thoroughly mixed condition. The dates on the Bass Diabase Sill and Grand Canyon are contradictory, and or discordant, and I'd found these in other materials that I've dated. Here's the Bass Diabase Sill. The potassium argon isochron, a whole rock isochron, gave an age of 0.84 billion years. The rubidium strontium isochron, which is the currently accepted age among the establishment geologists for the Bass Diabase Sill, is 1.06 billion years, with a rather small error bar. And so that has been suggested to be the age. Originally, when the first dates were published, potassium argon dates were there about 800 million years. And that was okay because it sat underneath the Tapete sandstone, and so it gave a Precambrian date. And so the evolutionary establishment originally could live with an age that way. When the first isochron, rubidium strontium isochron, was published 1.06 billion years, that was immediately accepted, and the potassium argon was rejected. I've dated whole rocks from the sill. 11 whole rocks form a really nice lead-lead isochron, suggesting an age of 1.2 billion years. The error bars seem to be discordant with the 1.06 billion year. And then the Sumerian neodymium method gives about just a little shy of 1.4 billion years. And what is interesting is that the 4 dating methods should give the same age, exactly the same age. Within the error bars, they should all overlap. And what's happened is they haven't. And I've done other isochron dates and isochron plots, and similar orders found. What is the true age of the Bass Diabase Sill? Is it 0.84 billion years? Plus or minus maybe 150 million years? Is it 1.06 billion years, plus or minus about 50 million years? Clearly discordant with that one over there. Okay, is it 1.2 billion years? A is 0.84, B 1.06, C 1.2 billion years. That's the lead-lead isochron. Or D 1.4 billion years, the Sumerian neodymium isochron, again with a little more than 100 million year error bars. Or E, what would E be? None of the above, okay? Now here's what I could argue. I can argue none of the above. None of the above, there we go. Could that be the answer to this question? What is the true age of the diabase sill at Bass Rapids and in Grand Canyon? Now, I plotted this. You want to see error bars and some of the technical data. It looks like the potassium-argon dates, those are 2 sigma error bars, so it's 95% chance it's within that error range. Here's that 800 million year age. The rubidium strontium is tightly constrained, somewhere around 1.05 billion years. And the lead is, we're currently refining the error bars on this, but it's somewhere around a little more than 1.2 billion years. And the Sumerian neodymium is up there close to almost 1.4 billion years. The error bars of Sumerian neodymium don't overlap the rubidium strontium, and so there seems to be discordant dates. So I haven't hit a home run, but I'm on first base. I can argue none of the above, can't I? Now here's what I could do. I can propose a model that could explain how to make these concordant. We could have alpha decay accelerated more than beta decay. Do you see what I have here? And I've plotted half-life. And it could be that the alpha decay has been accelerated more than beta decay, and that the higher the half-life, the higher the rate of acceleration of radioisotope decay. And the beta decay the same way. The higher the half-life, the higher the radioisotope accelerated decay. So that's kind of what I'm thinking. And I'm trying to explain why the dates don't agree. And in other rocks, I've seen the same phenomena. The beta decay ages are less than the alpha decay ages, and they seem to be in order of their half-life. And so that is really interesting. And so we're actually going to do more mineral isochron and whole rock isochron on this diabase. The error bars are 2 sigma, so anybody dealing with this data would have to say it's evidence of discordance. Now, we might talk about, is there a physical process that can reset or alter these isochrons in the different mineral phases from their homogeneous condition, we suppose? I don't think well, let the storytelling begin, but this is not a dream come true for an evolutionist model for the concordance of Grand Canyon dates. I dated the lava dome at Mount St. Helens one day. Well, I was walking up in the crater, and I collected from the lava dome a sample of the dacite lava dome that was extruded 11 years before, and I took it back and I processed the mineral phases from it. An 11-year-old lava sample was dated by potassium-argon method. I dated the whole rock, and I dated the mineral phases. The whole rock age was 350,000 plus or minus 50,000 years. The mineral ages, individual minerals were separated out there. I dated those by the conventional potassium-argon method, gave ages up to 2.8 million years for an 11-year-old rock. By the way, I didn't fill out on the isotope form suspected age when I sent them in. They were blind. They didn't know what I was sending them. And a 2.8 million year orthopyroxene minerals inside the lava dome. It looks like those minerals and the whole rock have in it a large amount of argon. The initial assumption of the argon method is there were no argon-40 originally in the lava when it crystallized 11 years ago on the lava dome. That's the problem. And obviously it's an error. And if you believe the potassium-argon dating methods can be applied widely to Grand Canyon rocks or anywhere, without critical evaluation. I've got a bridge I want to sell you because a lot of potassium argon dates are being thrown out. Many of the laboratories that are doing potassium argon dates have quit. They're just not doing them anymore. And so this method is being largely ignored and explained away. Lava dome dates. Helium in biotite and zircon. The helium in those zircon crystals seems to be there, a large part of it. The biotite crystal has a small mineral inclusion, zirconium silicate or zircon in it, and inside there is thorium and uranium, and the radioisotope transmutation creates helium. Here's a zircon crystal, and they're very beautiful crystals. They're very high temperature minerals, so they don't easily melt, and the lattice structure retains a lot of helium. And remember that what Dr. Vardaman said, helium leaks out very easily. It's lightweight, it's fast moving and slippery, and over billions of years, there should be a very low quantity of helium in the zircons. It should be in the atmosphere. Instead, we find very little helium in the atmosphere, and we think a large part of the crust of the Earth has lots of helium stored in it. It wiggles through crystals and it leaks through cracks in the crystals, but it seems to still be there. In other words, its rate of diffusion is high, and yet it's still there. That could be an argument for young zircons or accelerated radioisotope decay. Well, why did I once believe in an old Earth? Okay, and that's interesting, isn't it? Now, those are the reasons I believe in a young Earth. I think radioisotope dating can be interpreted in a young Earth context, along with those other things. A lesson from radioisotope dating. Did I learn this? This is what I learned. I think this is the story. Data are interpreted two different ways. Like I once had an evolutionary interpretation, now I have a creationist interpretation of the data. Bias A goes through the data to interpretation A. Bias B goes through the same data to a different interpretation. So we learn that our presuppositions and what we suppose about things get involved with our ideas of the age of things. A young Earth interpretation is being generated for radioisotope abundances. That's what the RATE project's doing. Okay, well I've essentially finished my lecture and well ahead of time because I think we've had a significant day. If you want to talk to me about this lecture, I'll stick around after the lecture, but you have a good evening, and I'm going to turn it back to the convener, sir.